Welcome to Dreaming Through Knowledge, where science becomes calm. Tonight, we embark on a voyage that spans both the unimaginable scale of the cosmos and the microscopic precision of the quantum world. We are going to follow the quiet, eternal journey of a single particle of light. But before we ignite the first spark, I invite you to subscribe to this channel and perhaps leave a comment below. Tell us where you are listening from tonight and what time it is in your part of the world. It is a small way for us to connect across the distance, much like the light we are about to explore. Now, let your body settle. Let the weight of the day fall away. Close your eyes and let your imagination drift inward, then outward, leaving the earth behind. We are traveling to a place of intense heat and pressure, a place where matter is transformed into energy. We are traveling to the heart of a star. Imagine the sun. From Earth, it is a perfect yellow disk, warm and steady in the sky. But if we could fly closer, if we could peel back the layers of blinding plasma, we would find a machine of terrifying power. We must go deep. We must pass through the corona, the chromosphere, and the photosphere. We must sink through the boiling convection zone and the silent, dense radiative zone. We arrive at the core. This is the engine room of the solar system. It is a sphere roughly 1/5 the size of the star, yet it contains half of its mass. The density here is extraordinary, 150 times the density of liquid water. It is 10 times denser than lead. The atoms are packed so tightly that they have no room to move. The temperature is 15 million degrees Celsius. In this crushing heat, matter as we know it cannot exist. The atoms are stripped of their electrons. They become a plasma, a soup of naked nuclei and free-floating electrons, buzzing with electrical charge. It is a chaotic, violent ocean of particles. Here, in the dark, the most important event in the universe takes place: nuclear fusion. It is the alchemy that turns matter into light. The core is filled with hydrogen nuclei, single protons. These protons are positively charged. And as we know from basic physics, like charges repel. If you try to push the north poles of two magnets together, you feel a force pushing back. The same is true for protons. This is the Coulomb barrier. As two protons rush toward each other in the thermal frenzy of the core, they feel this repulsive force. It acts like a force field. The closer they get, the stronger it pushes back. They slip, they slide, they refuse to touch. Even at 15 million degrees, the protons are not moving fast, enough to overcome this barrier through brute force alone. According to classical physics, they should bounce off each other every time. They should never fuse. The star should never ignite. The universe should be cold and dark. But the universe has a secret. It has a loophole. It uses quantum mechanics. In the quantum world, a proton is not a hard, solid ball. It is a wave. It is a fuzzy cloud of probability. It doesn't have a precise location. It has a likelihood of being in many places at once. Because the proton is a wave, it doesn't have clear edges. When two protons get close to the Coulomb barrier, their waves overlap slightly. There is a tiny, infinitesimal chance that the proton can simply appear on the other side of the barrier without actually having the energy to climb over it. This is called quantum tunneling. It is as if you threw a tennis ball at a brick wall, and once in a trillion throws, it simply passed through the bricks and appeared on the other side. It is an incredibly rare event. For any single pair of protons in the Sun, the chance of tunneling and fusing is astronomically low. A single proton could bounce around the core of the Sun for billions of years and never fuse. But the star has numbers on its side. The core of the star is packed with septillions of protons. They are colliding billions of times every second. So even though the probability is tiny, the sheer number of collisions ensures that it happens. It happens often enough to power a solar system. When two protons finally tunnel through the barrier and touch, the strong nuclear force takes over. This is the strongest force in the universe, but it only works at extremely short range. It snaps the two protons together like a vise. This is the moment of ignition. This is the spark. But the process is not done. Two protons cannot just stick together. They are unstable. One of them must change its nature. In a moment of weak nuclear magic, one proton sheds its positive charge. It emits a positron and a neutrino. It transforms into a neutron. Now we have a pair. One proton and one neutron bound together. This is deuterium, or heavy hydrogen. The deuterium is quickly hit by another proton. They fuse to form helium-3. And finally, two helium-3 atoms slam together to form helium-4, the stable ash of the nuclear fire. This complex dance is called the proton-proton chain. It is the engine of our Sun. But why does it produce light? Why does it make the stars shine? It comes down to mass. If you weigh the 4 protons that went into the reaction, and then you weigh the helium nucleus that came out, you find something strange. The helium is lighter. It weighs about 0.7% less than the ingredients. Matter has disappeared. It has vanished from existence. Where did it go? It turned into energy. This is Einstein's revelation. E Schattacker MC2. Energy equals mass times the speed of light squared. Because the speed of light is a huge number, a tiny amount of mass creates a colossal amount of energy. That missing 0.7% of mass is released as a flash of pure gamma radiation. A photon is born. This is our protagonist, a single packet of energy, born in the deepest violence imaginable. It is a gamma ray, the most energetic form of light. It is blue, fierce, and deadly. If you were exposed to it, it would tear your DNA apart. This newborn photon begins its journey. Its destination is the surface of the Sun, and then the Earth. The distance from the center of the Sun to its surface is about 700,000 kilometers. At the speed of light, it should take 2 seconds to cross. But it does not take 2 seconds. It takes 100,000 years. This is the great struggle of the light. The core of the Sun is incredibly dense. It is crowded. The photon cannot move in a straight line. It travels a tiny fraction of a centimeter and, smack, it hits a proton. It is absorbed. The proton shudders with the energy and then spits the photon out again, but it spits it out in a random direction. Maybe forward, maybe backward, maybe sideways. The photon travels another tiny distance. Smack. Another collision. Another random redirection. This is called the random walk, or the drunkard's walk. Imagine being lost in a dense forest at night, bumping into trees every step, turning round, retracing your path. That is the life of the photon in the core. It is pinballing through the dense plasma, taking billions of steps just to move an inch. It is a labyrinth without walls. The photon might spend 1,000 years just circling the center, making no progress at all. It is trapped in a game of chance, as it fights its way outward, slowly migrating from the core to the radiative zone. It changes. Every collision steals a little bit of its energy. The proton that absorbs it heats up, and when it re-emits the photon, it emits it with slightly less energy than before. The violent gamma ray is stretched. It becomes an X-ray. It becomes an ultraviolet ray. It is aging. It is cooling down. By the time it reaches the upper layers of the sun, the convection zone, the plasma is churning like boiling water. Giant bubbles of hot gas rise to the surface, carrying the light with them. The journey accelerates. Finally, after millennia of struggle, the photon reaches the photosphere. This is the visible surface of the sun. The density drops. The crowd thins out. The path ahead is clear. In one last interaction, the atom releases the photon. It is no longer a gamma ray. It has been tamed. It is now a particle of visible white light. It is free. It launches into the vacuum of space, and now, for the first time in its long life, it can show its true nature. It accelerates instantly to the cosmic speed limit, 300,000 kilometers per second. It does not need to build up speed. Light is born moving at top speed. It cannot go slower. If it exists, it moves. It crosses the distance from the sun to the Earth, 150 million kilometers, in 8 minutes and 20 seconds. It flies past Mercury, scorching the rocks. It flies past Venus, reflecting off the thick white clouds. It races through the silence of the void. Space is empty. There are no protons to hit, no friction. The light travels in a perfect straight line, a wave of electric and magnetic energy oscillating in harmony. It carries the news of the sun. It carries the heat that will drive the wind and the weather. Then it hits the atmosphere of Earth. The journey changes again. The vacuum ends. The air begins. The atmosphere is a blanket of nitrogen and oxygen molecules. As the white light of the sun hits these molecules, it scatters. The white light is made of all colors: red, orange, yellow, green, blue, indigo, violet. Each color has a different wavelength. Blue light moves in short, choppy waves. Red light moves in long, lazy waves. The short blue waves crash into the nitrogen molecules and scatter in every direction. They bounce around the sky, painting the dome blue. The longer red and yellow waves are able to dodge the molecules, passing through relatively straight. This is why the sky is blue and the sun looks yellow. It is a trick of scattering. At sunset, the light has to travel through much more air to reach your eye. Most of the blue is scattered away completely, leaving only the deep reds and oranges to touch the clouds. But let us follow a single photon that makes it through the blue haze. It falls downward, through the clouds, through the leaves of a tree, and lands on a surface. Let us say it lands on the leaf of a fern in a forest. This moment is the foundation of all life on Earth. The photon strikes a molecule of chlorophyll within the leaf. The energy of the light knocks an electron loose. This captured energy is used to split a water molecule, releasing oxygen and creating sugar. This is photosynthesis. It is the process of turning light into food. Every apple you eat, every slice of bread, every piece of meat, it is all stored sunlight. The energy that moves your muscles right now is the same energy that was forged in the core of the sun 100,000 years ago, traveled across space, and was caught by a plant. We are light eaters. Or perhaps the photon does not hit a leaf. Perhaps it hits something else. Perhaps it hits your eye. You are standing in a garden. The photon passes through the clear window of your cornea. It swims through the fluid of your eye. It passes through the lens, which focuses it, and it strikes the retina at the back of your eye. The retina is a carpet of sensitive cells, rods and cones. Inside one of these cells, there is a protein called rhodopsin. When the photon hits the rhodopsin, the protein changes shape. It snaps. This microscopic movement triggers a chemical cascade. It generates an electrical impulse. The impulse travels down the optic nerve into the dark interior of your brain, to the visual cortex. Your brain receives the signal and says, light. It says, green. It constructs an image. The world you see, the colors, the shapes, the faces of your loved ones, is a reconstruction happening inside your head, built from the impacts of billions of photons. Vision is the sense of touching the universe from a distance. When you look at a star, your eye is physically touching a photon that has traveled for 1,000 years just to end its life on your retina. It is a form of intimacy with the cosmos. In the next chapter, we will stay within the sun for a little longer. We will explore the strange, silent journey through the radiative zone in more detail. We will look at the plasma ocean. We will look at the randomness of the path. We will understand why the light of the sun is actually thousands of years old by the time it reaches the surface. We will explore the concept of the opacity of the star. For now, imagine the single photon, newly born in the core, a spark of gamma radiation, fierce, bright, and trapped, beginning its long, winding walk toward the freedom of space. We have witnessed the moment of creation. Deep in the crushing heart of the star, protons have fused, mass has vanished, and a single packet of pure energy, a photon, has been born. It is a gamma ray, fierce and blue, vibrating with the raw power of the nuclear furnace. It is moving at the speed of light, 300,000 kilometers per second. At this speed, it should reach the surface of the sun in 2 seconds. But it does not. The photon is alive, but it is not free. It has been born into a prison of unimaginable density. The core of the star is packed so tightly with matter that it is 10 times denser than lead. To the photon, this is not empty space. It is a solid wall of charged particles. The journey that should take a heartbeat will instead take an eternity. The photon travels only a fraction of a millimeter before it crashes. It slams into an ion, a proton, or a free electron. It is absorbed. The energy is taken into the particle, causing it to vibrate, to heat up. For a tiny sliver of time, the photon ceases to exist as a separate entity. It is just energy trapped in matter. Then the particle relaxes. It spits the photon back out. But here is the cruelty of the physics. The particle has no memory of direction. It does not know that the photon wants to go out toward the surface. It emits the new photon in a completely random direction. It might send it forward, but it is just as likely to send it sideways or backward, back toward the center of the star. The photon moves again. It travels another fraction of a millimeter. Smack. Another collision. Another absorption. Another random redirection. This is the random walk. It is the drunkard's walk. Imagine a person lost in a dense, endless forest in the middle of the night. They take a step, bump into a tree, turn around, take another step, bump into another tree. They are moving constantly, but they are getting nowhere. This is the reality of light inside a star. The photon is pinballing through the plasma. It is trapped in a game of chance, played on a scale that defies comprehension. To move just 1 meter from the center might take 1 billion collisions. To move 1 kilometer might take 1 trillion. For thousands of years, the photon remains trapped in the deep core. It circles the center, revisiting the site of its own birth over and over again. It is a prisoner of the density. It is a strange paradox. The fastest thing in the universe is stuck in the slowest journey imaginable. But slowly, statistically, the photon makes progress. It drifts outward. As it moves away from the center, the conditions begin to change. The temperature drops. In the core, it was 15 million degrees. As the photon climbs into the radiative zone, the temperature falls to 10 million, then 5 million degrees. The pressure eases slightly. The density drops. The distance between collisions grows from 1 millimeter to 1 centimeter. The photon can breathe a little, but this freedom comes at a cost. Every time the photon collides with a particle, it loses a tiny amount of energy. The particle steals a fraction of the photon's heat. This scattering changes the nature of the light. It stretches the wavelength. The photon began its life as a high-energy gamma ray, a lethal, invisible scream of radiation. But as it fights its way through the radiative zone, it is softened. It becomes an X-ray. It becomes extreme ultraviolet. It is aging. The fierce, sharp energy of its youth is being worn down by the endless friction of the passage. It is being domesticated. This process is essential for life. If the sun released the gamma rays directly from the core, they would sterilize the Earth. The random walk acts as a shield, a filter that converts the deadly nuclear fire into gentle warmth. This region, the radiative zone, extends for about 70% of the sun's radius. It is a place of profound silence. There is no churning here. The gas is stable. It is like a vast, glowing ocean that is perfectly still, transferring heat only through this slow bucket brigade of photons handing energy to one another. This journey takes time, a long time. Estimates vary, but it can take anywhere from 100,000 to 1,000,000 years for a photon to navigate this zone. Think about that. The light that is hitting your eye right now as you look out the window was created in the core of the sun before human civilization existed. It was born when our ancestors were painting in caves, or perhaps even before our species evolved. It has been wandering in the dark labyrinth of the sun for aeons, trying to find the door. It is ancient light. It is a fossil of energy from the deep past. But eventually, the physics changes. The photon reaches a boundary layer about 200,000 kilometers below the surface. This is the tachocline. It is the transition zone. Here, the calm, radiative transfer of energy stops working. The gas becomes too cool, only 2 million degrees. It becomes opaque. The photons can no longer push their way through the crowd. They get stuck. The energy piles up at the bottom of this layer like water behind a dam. The heat builds, and when a fluid is heated from below and cannot radiate its heat away, it begins to boil. The sun begins to churn. We enter the convection zone. The environment shifts from a silent, static ocean to a roaring, boiling cauldron. Giant bubbles of hot plasma, thousands of kilometers wide, detach from the bottom layer. They are buoyant. They rise upward, carrying the heat and our trapped photons with them. The photon is no longer walking, it is riding an elevator. It is swept up in a plume of superheated gas, rushing toward the surface at supersonic speeds. It is a chaotic ride. The plasma is turbulent, twisting and turning, generating massive magnetic fields that snap and crackle. This is the loudest part of the sun. If sound could travel through space, the roar of the convection zone would be deafening even on Earth. The sun rings like a bell, vibrating with the acoustic energy of these rising bubbles. The photon is carried through this cacophony, trapped inside the bubble of plasma. As the bubble rises, it expands, it cools. But it is still hotter than the surrounding gas, so it keeps rising. It climbs for a month, carried by the currents of the star. Finally, it nears the top. The density drops precipitously. The gas becomes thin. We are reaching the photosphere, the sphere of light. This is what we see as the surface of the sun. It is not a solid surface. You could not stand on it. It is simply the point where the gas becomes transparent. It is the edge of the fog bank. The bubble of hot gas breaches the surface. It spreads out, releasing its heat into the cold void of space. And in that release, the photon is finally liberated. For 1,000,000 years, it has been bumping into things. It has been absorbed and re-emitted trillions of times. It has forgotten its direction. It has changed its color. It has aged. But now, looking up, there is nothing in its way. The path ahead is clear. There are no more protons to block it, no more electrons to scatter it. There is only the infinite empty vacuum. The photon launches. In an instant, it accelerates to its maximum velocity. It does not need to speed up. Light is born moving at top speed. It is traveling at 299,792,458 meters per second. It is the fastest thing in existence. It leaves the surface of the star. It flies past the ghostly white halo of the corona, the sun's outer atmosphere, where the temperature inexplicably spikes to 1,000,000 degrees. It dodges the magnetic loops and solar flares that arch high into the black sky. It is free. It has changed since its birth. It is no longer a deadly gamma ray. It has been stretched by its long struggle into a visible photon. It might be yellow, it might be green, it might be red. It joins countless others, a tsunami of light rushing outward in a sphere of brilliance. The sun loses 4,000,000 tons of mass every second in the form of this light. It is evaporating. It is pouring itself out into the universe. Our photon is one tiny drop in that flood. Behind it, the star rages on. The bubble of gas that delivered the photon cools down. It becomes dark and dense. It sinks back down into the depths of the convection zone to be reheated and start the cycle again. But the photon never looks back. It has a destination. It enters the realm of interplanetary space. To us, this looks empty. But to a photon, it is still a landscape. There is the solar wind, a stream of charged particles blowing out from the sun. There is dust left over from comets. There are magnetic fields. But compared to the interior of the sun, this is emptiness. The photon travels in a perfect straight line. It does not experience time. This is one of the strangest truths of relativity. For us, watching the photon, its journey takes time. We can measure it. But for the photon itself, the journey is instantaneous. Because it travels at the speed of light, time dilation is infinite. The moment it leaves the surface of the sun and the moment it hits the earth are the same moment. For the photon, the universe has zero depth. It connects the source and the destination instantly. It is a bridge of pure simultaneity. But to us, waiting on Earth, there is a delay. We are 150 million kilometers away. We are one astronomical unit, AU, from the fire. It takes the photon 8 minutes and 20 seconds to cross this gap. 8 minutes. It flies past the planet Mercury. Mercury is blasted by the light. It has no atmosphere to protect it. The rocks on the day side are baked to 400 degrees Celsius. The photon illuminates the craters, the ancient scars of the solar system. It flies past Venus. Venus is wrapped in a thick blanket of white clouds. The photon hits the clouds and bounces off. It reflects. This is why Venus looks so bright in our night sky. It is a mirror. The photon glances off the world and spins away into the deep dark, destined to travel forever until it hits something else. Perhaps a distant nebula or an alien eye. But our photon is not aimed at Venus. It is aimed at the third rock, the blue marble. It approaches Earth. From a distance, the planet looks peaceful, a sphere of blue water, white swirls of cloud, and continents of brown and green. It looks quiet, but as the photon gets closer, it encounters the first line of defense, the magnetosphere. The Earth is a giant magnet. Invisible lines of force loop out from the poles, creating a shield against the solar wind. The photon, being neutral, ignores this shield. It passes right through the magnetic field lines. It is not a charged particle. It is light. It cannot be deflected by magnetism. But then it hits the atmosphere. For the first time in 8 minutes, the vacuum ends. The photon encounters matter again, the air, a mixture of nitrogen, oxygen, argon, and trace gases. The atmosphere is a filter. It is a prism. It is a shield. When the wave front of sunlight hits the top of the atmosphere, it begins to scatter. This phenomenon is called Rayleigh scattering. The molecules of nitrogen and oxygen are very small. They are roughly the same size as the wavelength of blue light. Because of this match in size, the blue photons, the high-energy, short waves, crash into the molecules and bounce off. They scatter in every direction. They pinball around the sky. This is why the sky is blue. When you look up, you are not seeing the black of space. You are seeing billions of scattered blue photons dancing in the air. The atmosphere catches the blue light and holds it, painting the ceiling of the world. But the red, yellow, and orange photons have longer wavelengths. They are too big to be bothered by the small gas molecules. They step right over them. They pass through the atmosphere relatively straight. This is why the sun looks yellow to us. It is white light minus the blue. And at sunset, when the sun is low on the horizon, the light has to travel through much more air to reach your eye. The path is longer. More and more blue light is scattered away. Then the green is scattered. Then the yellow. By the time the light reaches you, only the longest, most stubborn wavelengths remain, the deep reds and oranges. The sunset is the survivor light. It is the light that endured the longest journey through the air. But let us assume our photon is not scattered. Let us assume it is a lucky photon. It passes through the ozone layer in the stratosphere. The ozone layer is a thin shield of O3 molecules. It has a specific job, to hunt ultraviolet light. If our photon were an ultraviolet photon, the ozone would absorb it, sacrificing itself to protect the surface. This absorption heats the stratosphere. But our photon is visible light. It passes through the ozone safely. It falls through the troposphere, the layer of weather. It dodges the water droplets in the clouds. Clouds are white because water droplets are big. they scatter all colors equally. If our photon hit a cloud, it would bounce around inside the mist, turning the cloud into a glowing box of light, before eventually falling out the bottom as diffuse gray light. But today, the sky is clear. The photon falls the last few kilometers. It rushes toward the ground. It has traveled from the core of the sun. It has spent 1,000,000 years in the dark labyrinth. It has crossed the cold void of space. It has navigated the blue maze of the atmosphere. And now it is about to end its journey. It is about to hit something. Perhaps it hits a solar panel. It strikes a silicon atom, knocking an electron loose, creating a current of electricity that flows into a battery, storing the energy of the star to light a house at night. Perhaps it hits the ocean. It penetrates the water, traveling down into the blue depths, finally being absorbed by a water molecule, adding a tiny amount of heat to the global sea, driving the currents that regulate our climate. Or perhaps it hits a leaf. This is the most magical destination. The photon strikes a molecule of chlorophyll in the leaf of an oak tree. The energy is captured. It is not lost as heat. It is used to do work. It splits water. It builds sugar. It turns light into wood, into fruit, into oxygen. The photon dies so that the tree can live. The energy that was born in fusion becomes the energy of life. In the next chapter, we will explore the other destiny of light. We will look at what happens when the photon does not hit the Earth. What happens to the light that misses? We will follow the light that travels past us, out into the deep universe. We will see how it travels for billions of years, crossing the voids between galaxies. We will see how it stretches as the universe expands, becoming redder and redder. We will look at the light that becomes a messenger from the past, carrying images of ancient galaxies to the mirrors of our telescopes. We will see how light allows us to look back in time. For now, feel the warmth of the sun on your skin, or imagine it in your mind. That warmth is the touch of the photons we have just followed. It is a physical connection to the heart of the star. You are being touched by energy that is 1,000,000 years old. Rest in that warmth. You are the destination. We have witnessed the destiny of the lucky photons, the ones that found a home on the retina of an eye or the surface of a leaf. But for every photon that strikes the Earth, billions upon billions miss. They pass by our blue marble in the silence of the vacuum, continuing their journey outward. Tonight, we follow them. We leave the warmth of the inner solar system and head for the deep cold. As our photon flies past Earth, the planet recedes. It becomes a crescent, then a sphere, then a bright blue star, and finally, a speck of dust suspended in a sunbeam. The photon is traveling at the speed of light, yet the distances it must now cross are so vast that even light seems to crawl. The first landmark on this outward trajectory is Mars. It takes the light about 12 minutes to reach the red planet, depending on the orbital alignment. Mars appears as a rusty beacon in the dark. It has a thin atmosphere, barely a whisper of gas compared to Earth, made mostly of carbon dioxide. When our photon hits the dust storms of Mars, it reflects a specific wavelength, red. The iron oxide on the surface absorbs the blues and greens, rejecting the red light back into space. This is the blood-red signature of the war god. But Mars is cold. The sun here is dimmer, smaller. The energy reaching the surface is less than half of what we receive on Earth. Past Mars, the photon enters the asteroid belt. We often imagine this as a crowded field of tumbling rocks, like a scene from a movie. But space is huge. The asteroids are millions of kilometers apart. Our photon flies through this region without ever touching a stone. It navigates the silence between the ruins of a planet that never formed. It travels for another 30 minutes. The sun behind it is shrinking. It is becoming a brilliant, piercing point of light rather than a disk. And then, looming out of the darkness, comes the king, Jupiter. Jupiter is a monster. It is more massive than all the other planets combined. It is a ball of gas, hydrogen, and helium, so compressed that it behaves like a liquid metal deep inside. But to our photon, arriving from the sun, Jupiter presents a face of swirling clouds. These clouds are made of ammonia crystals and sulfur. They are painted in bands of cream, ochre, and brown. The photon strikes the cloud tops. It bounces off the white zones, reflecting almost all the energy. It gets absorbed in the dark belts. It might hit the Great Red Spot, a storm that has been raging for 300 years, wider than the Earth itself. The reflection of sunlight off Jupiter is intense. It makes the planet shine like a diamond in our night sky. But there is something strange happening here. Jupiter emits more energy than it receives from the sun. It is still glowing with the primordial heat of its formation. It is almost a star. Our photon mixes with this internal heat, a blend of ancient and new light. Around the giant, a miniature solar system orbits, the Galilean moons, Io, volcanic and yellow, Europa, an ice ball covering a global ocean, Ganymede and Callisto, cratered and ancient. Our photon might strike the ice of Europa. If it does, it penetrates the ice for a few centimeters before being scattered. It illuminates the frozen crust, beneath which lies more water than all the oceans of Earth combined. It is a tantalizing thought. Sunlight touching the roof of a potential habitat for life, billions of miles from the habitable zone. But the photon does not stop. It flies on. It has been traveling for over an hour now. The sun is far away. The temperature of space is dropping. We are crossing the gap to the next giant, Saturn. Saturn appears as a golden jewel, surrounded by the most spectacular structure in the solar system, the rings. These rings are not solid. They are made of trillions of particles of water ice, ranging from the size of a grain of sand to the size of a house. They are the shattered remains of a moon that wandered too close and was torn apart by gravity. When our photon hits the rings, it hits a mirror. The ice is pristine. It reflects the sunlight with dazzling efficiency. This is why Saturn creates such a sense of wonder. It is a sculpture made of light and ice. Imagine floating in the shadow of Saturn. The sun is eclipsed by the planet, but the rings are backlit. They glow with a ghostly, ethereal light, scattering the sunbeams through the dust. It is a cathedral of geometry. Our photon dances through this dust, bouncing from ice crystal to ice crystal, before escaping back into the void. The journey continues. The distances are becoming difficult to comprehend. It takes the light nearly 3 hours to reach Uranus and 4 hours to reach Neptune. These are the ice giants. They are cold, blue worlds wrapped in thick atmospheres of methane. Why blue? Because methane absorbs red light. When our photon dives into the atmosphere of Neptune, the red part of its energy is eaten by the gas. Only the blue light is scattered back out. It is the same physics that makes the Earth's sky blue, but played out in a deep, frozen slush of hydrocarbons. Here, the sun is just a very bright star. It provides almost no heat. The temperature is 200 degrees below zero. The light is weak. It is twilight all the time. Noon on Pluto is no brighter than dusk on Earth. This dimming is caused by a fundamental rule of geometry, the inverse square law. Imagine a balloon expanding. The rubber gets thinner as it stretches. Light behaves the same way. As the sphere of light emitted by the sun expands, the photons spread out. If you double the distance from the sun, the light doesn't get half as dim. It gets 1/4 as bright. If you triple the distance, it gets 1/9 as bright. By the time you reach Neptune, 30 times further from the sun than Earth, the sunlight is 900 times fainter. The energy is spreading thin, diluting into the vastness of space. The warmth that fueled the forests of Earth is gone. There is only a cold, hard illumination. We pass the orbit of Neptune. We enter the Kuiper Belt. This is the junkyard of the solar system. Billions of frozen rocks, comets, and dwarf planets drift here in the dark. Pluto, Eris, Makemake. They are the leftovers of creation, untouched for 4 billion years. Our photon flies past these silent sentinels. It illuminates the nitrogen glaciers of Pluto for a fraction of a nanosecond, and then moves on. There is nothing to stop it now. The gaps between objects are increasing. The solar system is fading, but we are not quite out yet. The sun has a reach that extends far beyond the planets. It breathes out a stream of charged particles, the solar wind. This wind blows a giant bubble in the interstellar medium. This bubble is the heliosphere. For hours, days, our photon travels through this bubble. It is flying through the tenuous atmosphere of the sun itself. But eventually, it reaches the edge, the heliopause. This is the boundary where the pressure of the solar wind is finally stopped by the pressure of the galaxy. It is the border of the sun's domain. In 2012, the Voyager 1 spacecraft crossed this line. It sent back a signal, weak radio frequency photons, telling us that the plasma density had changed. It had left home. It had entered interstellar space. Our photon crosses this line without slowing down. It leaves the protection of the sun. It enters the interstellar medium. This is the space between the stars. It is not truly empty. It is filled with a thin mist of hydrogen gas, dust, and high-energy cosmic rays. But it is thinner than any vacuum we can create on Earth. An atom here might travel for years before hitting another atom. Here, the sun is nothing more than the brightest star in the sky. It has lost its dominance. It is just one point of light among billions. The photon is now a cosmic traveler. It is no longer sunlight. It is just starlight. It carries the spectral fingerprint of the sun, the specific mix of colors that identifies it as a yellow dwarf star, out into the galaxy. This light is a message. It says, there is a star here. It is made of hydrogen and helium. It has this temperature. It has this age. If there is an alien astronomer sitting on a planet orbiting Alpha Centauri, looking at our sun through a telescope, they catch these photons. They pass the light through a prism. They see the spectrum. They read the barcode of our home. But Alpha Centauri is 4 light years away. That means our photon has to travel for 4 years to get there. 4 years. Think of what happens on Earth in 4 years. Governments change. Children learn to read. Seasons cycle 16 times. All that time, the photon is flying through the dark, silent void, never slowing, never stopping, never changing. To the photon, as we know, no time passes. It is born, and it arrives. But to us, the gap is enormous. The distance is 25 trillion miles. This distance is the fundamental barrier of the universe. It isolates us. It makes conversation with the cosmos agonizingly slow. "Hello," we ask. 4 years later, the message arrives. "Hello," they reply. 4 years later, we hear it. A conversation taking a decade. And Alpha Centauri is the nearest neighbor. The next stars are tens, hundreds, thousands of light years away. As the photon travels deeper into the galaxy, it joins the great river of starlight. The Milky Way is a disk of 400 billion stars, all pouring photons into the void. This collective light creates the diffuse galactic background. It is the faint glow of the night sky between the stars. Our photon might travel for 1,000 years. It might pass through a nebula, a cloud of dust and gas where new stars are being born. If it does, it might be absorbed by a grain of dust. The dust grain warms up. It re-emits the energy as infrared light. This is how we see nebulas glowing in the dark. They are repurposing the light of distant stars. Or perhaps our photon is lucky. It threads the needle. It avoids the dust. It avoids the planets. It avoids the other stars. It reaches the edge of the galaxy. The Milky Way is a spiral, a flat disk with bulging arms. Our photon travels upwards out of the plane of the disk. It rises above the galaxy. From this vantage point, the view is breathtaking. The entire galaxy is laid out below, a swirling pinwheel of light, a city of stars rotating slowly in the dark. Our sun is just one tiny window light in this metropolis. The photon continues to climb. It passes the halo, a sphere of old stars and globular clusters that surrounds the galaxy like a swarm of bees. And then it enters the intergalactic void. This is the true emptiness, the space between galaxies. It is a darkness so profound that the human mind cannot grasp it. The density of matter here is less than 1 atom per cubic meter. It is the closest thing to nothing that exists in nature. Here, the photon will travel for millions, perhaps billions of years. It will fly through the dark, carrying the image of our sun long after our sun has died. This brings us to the concept of the light cone. Every event in the universe, a match being struck, a star exploding, a child smiling, sends out a sphere of light. This sphere expands at the speed of light. It gets bigger and bigger, encompassing more and more of the universe. Inside the sphere, the event is visible. Outside the sphere, the event has not happened yet. The news hasn't arrived. Our photon is the leading edge of the sun's light cone. It is expanding into the universe, carrying the causal history of our solar system. It defines the region of space that can know about us. If there's an observer in the Andromeda galaxy, 2.5 million light-years away, they are currently seeing our sun as it was 2.5 million years ago. They are seeing the Earth before humans. They are seeing the Pleistocene. They cannot see the Great Wall of China. They cannot hear our radio broadcasts. That light, those radio waves, haven't reached them yet. They are outside our current light cone. To them, we do not exist. Not yet. We are trapped in our own time bubble, expanding at the speed of light. But as the photon travels through this intergalactic deep, something begins to happen to it. something caused by the structure of space itself. The universe is expanding. The fabric of space is stretching. And as the space stretches, it stretches the photon. Imagine drawing a wave on a rubber band and then pulling the rubber band. The wave gets longer. The peaks get further apart. This is happening to our photon. Its wavelength is increasing. It is shifting toward the red end of the spectrum. It is losing energy. This is cosmological redshift. It is not caused by the photon hitting anything. It is caused by the growth of the universe. The photon is tired. It is aging in a way that only light can age, by changing color. If it travels long enough, billions of years, it will stretch from visible light into infrared, then into microwaves, then into radio waves. It will become invisible to biological eyes. It will become a ghost wave, drifting in the dark. This is the fate of all light in the universe. It is slowly being stretched into silence. The universe is cooling down, and the light is fading with it. In the next chapter, we will follow this ancient light. We will look at the photons that have been traveling not for years, but for eons. We will look at the light from the very first stars, the first light of the cosmos. We will see how astronomers use giant telescopes to catch these tired, stretched photons and reconstruct the history of the Big Bang. We will explore the cosmic microwave background, the afterglow of creation itself, which fills every cubic centimeter of space with a faint, archaic hum. But for now, drift with our photon in the space between the galaxies. The loneliness is absolute, but the purpose is clear. It is a messenger. It carries a packet of information. I was here, across the infinite gulf. It is a bridge between the past and the future. It is the memory of a star, written in energy, flying forever into the void. Rest in that vastness. The universe is huge and quiet and filled with light that is looking for a place to land. We have followed a photon from our own sun as it begins its eternal voyage outward, leaving the solar system to drift forever in the silence of the intergalactic void. But the story of light is not just about departure. It is also about arrival. Just as our solar photon flies out into the dark, countless others are flying in. The Earth is constantly bombarded by messages from the deep past. To understand the full scope of the story of light, we must reverse our gaze. We must look outward into the deepest wells of time. We must follow the journey of a photon that has been traveling not for minutes, but for eons. Imagine a time long before the Earth existed, long before the sun ignited. Go back 13 billion years. The universe is young. It is smaller, hotter, and crowded. The first galaxies are just beginning to form, violent, chaotic swirls of gas and fire lighting up the primordial darkness. In the heart of one of these infant galaxies, a massive star is born. It is a blue supergiant thousands of times brighter than our sun. It burns with a ferocious intensity, pouring out ultraviolet light into the fog of the early cosmos. Deep in the atmosphere of this ancient star, an electron jumps. It falls from a high-energy orbit to a low one. In that microscopic quantum leap, a photon is created. This photon is identical to the one we met in the sun. It is a packet of pure energy, but this one is born blue. It is a short, energetic wavelength vibrating with the fury of a young universe. It launches into space at the speed of light, heading outward. It leaves its home galaxy. It flies past the swirling clouds of gas that will one day form other stars. It dodges the dust. It escapes into the vast expanding emptiness between the islands of matter. Its destination, though it does not know it, is a small, rocky planet that will not be born for another 9 billion years. The journey begins. The photon travels for 1,000,000 years, then 1,000,000,000. It flies through the great voids, regions of space millions of light years across where there is nothing but a few stray atoms. It is a solitude so profound that the human mind cannot grasp it. But as it travels, something strange begins to happen. The ground beneath it is moving. The universe is expanding. Space itself is stretching. It is not that the galaxies are flying apart through static space. It is that the fabric of reality is growing, swelling like a balloon being inflated. New space is being created in the gaps between the galaxies. This expansion has a profound effect on our traveler. Light is a wave. It has a wavelength, the distance between two peaks. As the photon travels through the expanding universe, the space it travels through stretches, and because the light is embedded in space, the wave stretches with it. Imagine drawing a squiggly line on a rubber band. If you pull the rubber band, the squiggles get wider. The peaks move further apart. This is what happens to the light. Our photon started as blue light, tight, energetic waves. But as the billions of years pass, the wave is pulled apart. The wavelength gets longer. Blue light stretches into green. Green stretches into yellow. Yellow stretches into red. This phenomenon is called cosmological redshift. It is not the same as the Doppler shift of a passing siren. It is not caused by motion through space. It is caused by the expansion of space itself. It is a tired light. As the wavelength stretches, the energy of the photon drops. The universe is stealing its power. The fierce ultraviolet radiation of the young star is being tamed, cooled, and softened by the growth of the cosmos. The photon travels on. 5 billion years pass. The universe continues to grow. The photon is now infrared, invisible to the human eye, but still carrying the information of its birth. It is a ghost of heat flying through the dark. It encounters a massive structure in the distance, a cluster of galaxies, thousands of galaxies bound together by gravity, swarming like bees in a hive. This cluster is so massive, trillions of suns worth of mass, that it warps the fabric of space-time around it. It creates a gravity well, a deep dip in the mattress of the universe. Our photon is heading straight for it. According to Isaac Newton, light travels in straight lines. But as we learned, Albert Einstein showed us that mass curves space. Light has to follow the curvature. It has to follow the road. As the photon approaches the galaxy cluster, it feels the slope. It dives into the gravity well. It curves. Its path is bent, just as a lens bends light to focus it. This is gravitational lensing. The cluster acts as a natural telescope, a magnifying glass the size of 1,000,000 light years. It grabs the light from the distant background star and focuses it. Attachment. Attachment. Our photon is whipped around the side of the cluster. Its direction changes. Instead of flying off into the endless void, it is redirected. It is aimed. This bending of light does something extraordinary. It magnifies the image. It takes the faint, dying light of the ancient star and boosts it, making it brighter. It allows us to see things that are too small and too far away for any telescope to catch on its own. The universe provides the lens. We just have to provide the eye. The photon exits the cluster. It climbs out of the gravity well, losing a tiny bit more energy as it fights the pull. It resumes its straight-line journey, but now it is on a new trajectory. It is heading for a small, spiral galaxy that has recently formed in the distance, the Milky Way. Another 5 billion years pass. Our sun is born, the Earth forms, life evolves, dinosaurs rise and fall, the ice ages come and go. Humans look up at the sky and wonder. All this time, the photon is traveling. It crosses the intergalactic void, the great emptiness between the islands. It enters the halo of the Milky Way, a sphere of old stars and dark matter that surrounds our galaxy. It dives into the disk. The traffic increases. There are stars here and clouds of dust. Dust is the enemy of light. Interstellar dust grains, tiny specks of carbon and silicon, absorb visible light. If our photon were still visible light, it might be blocked. The galaxy would be opaque. But because our photon has been redshifted into the infrared, it has a superpower. Infrared waves are long. They are longer than the dust grains. They can wrap around the obstacles. They can slip through the clouds. The photon ghosts through the dusty pillars of the Milky Way, unseen and untouched. It enters the Orion Arm, a quiet suburb of the galaxy. It enters the solar system. It flies past Neptune, past Jupiter. It has been traveling for 13 billion years. It has crossed the entire observable universe. And now it has 1 second left. It is aiming for a specific point in space, a point located 1 million miles from Earth in a gravitationally stable pocket called Lagrange Point 2. Hanging there, suspended in the dark, is a machine, a giant gold-coated honeycomb, the James Webb Space Telescope. The telescope is looking at a patch of sky that appears empty to the naked eye. It is staring into the deep dark. Its 18 hexagonal mirrors are waiting. The photon strikes the gold. The mirror is cold, kept at minus 230 degrees Celsius, so that its own heat does not drown out the faint signal. The gold surface reflects the infrared photon perfectly. It bounces the photon to a secondary mirror, which focuses it into a cone of light. The photon travels down into the heart of the instrument, into a camera called NIRCam. It hits a detector, a chip of silicon and arsenic. Smack. The journey ends. The energy that was born in a blue supergiant 13 billion years ago is absorbed by a pixel. It knocks an electron loose. A tiny electrical signal is generated. Ping. The computer records the hit. It adds it to the count. 1 photon. But 1 photon is not enough to make an image. The telescope stares at the same spot for hours. It collects thousands, millions of these ancient travelers. They rain down on the mirror like a gentle, invisible drizzle. Slowly, an image builds up. A pattern emerges from the noise. When the astronomers on Earth download the data and process it, they see a miracle. In the patch of empty sky, a galaxy appears. It is a tiny red smudge, a blob of light. It doesn't look like much, but to the trained eye, it is a treasure chest. Because of the redshift, the astronomers know how far it is. They know this light has traveled for 13.2 billion years. They are looking at the universe as it was when it was a toddler. They analyze the spectrum of the light. They spread the infrared colors out, and they see gaps, dark lines in the rainbow. These are absorption lines. They are the fingerprints of chemical elements. As the light left the star, it passed through the star's atmosphere. The atoms in the atmosphere, hydrogen, helium, oxygen, absorbed specific wavelengths of light. By reading these missing lines, we can tell what the star was made of. We can do chemistry across space and time. We find that these ancient galaxies are different from ours. They have less metal. They are pristine. They are the first factories of the universe, just beginning the work of building the elements of life. This is the magic of the photon. It is a time capsule. It carries the history of its origin frozen within it. When you look at a photo from the James Webb Telescope, you are not looking at a static picture. You are looking at a collection of arrival times. The galaxy in the foreground might be 1 billion light years away. The galaxy behind it, 5 billion. The red smudge in the background, 13 billion. You are looking down a tunnel of time. You are seeing the history of the universe laid out in a single frame. You are seeing the evolution of structure. But there is a limit to how far back we can see. If we look past the first galaxies, past the first stars, we hit a wall. The cosmic dark ages we spoke of earlier, a time when there was no light sources. And if we look even further back, to 380,000 years after the Big Bang, we hit the wall of fog, the surface of recombination. The light from this wall is also arriving at Earth right now. It is coming from every direction at once. It is the cosmic microwave background. This light has been stretched the most. It started as visible orange light, the glow of the hot, cooling plasma. But the expansion of the universe has stretched it by a factor of 1,000. It is now microwaves. We cannot see it with our eyes, but we can see it with our radios. If you turn on an old analog television to a channel that doesn't exist, you see static, snow. About 1% of that snow is caused by the cosmic microwave background. You are watching the Big Bang on your TV. You are seeing the photons that were released when the universe first became transparent. You are watching the oldest light in existence. This light is the baby picture of the cosmos. It shows us the seeds of the galaxies. It shows us the density ripples that would eventually grow into the cosmic web. It confirms that the universe was once hot, dense, and uniform. It is the strongest evidence we have for the Big Bang theory, and it is brought to us by photons. Every second, day and night, this ancient rain of light falls on the earth. It passes through your roof. It passes through your body. You are constantly bathed in the afterglow of creation. It connects you to the beginning of time. But light does more than just carry images. It carries causality. In relativity, the speed of light is the speed of information. It is the maximum speed at which one thing can affect another. This creates a concept called the light cone. Attachment WAC 1, attachment. Imagine a cone extending backward from you into the past. This cone contains everything that could possibly have influenced you. Every star whose light has reached Earth. Every gravity wave that has passed through. Anything outside this cone is causally disconnected from you. It hasn't happened yet relative to you. You cannot see it, and it cannot hurt you. As time passes, your light cone grows. It swallows more of the universe. We are constantly seeing deeper. Every day, light from slightly further away reaches us for the first time. the observable universe gets a little bit bigger every second. We are expanding our bubble of knowledge at the speed of light, but there is a horizon. Because the universe is expanding and the expansion is accelerating, there are parts of the universe that are moving away from us faster than the speed of light. The light from these regions will never reach us. It is trying to swim upstream against a current that is moving too fast. It will be swept away into the dark. There are galaxies that we can see today that will one day cross this horizon and vanish. They will fade from view as their light is stretched to infinity. We are living in a privileged time, a time when the sky is full of galaxies, a time when the history of the universe is accessible to us. In the far distant future, the sky will be dark. The evidence of the Big Bang will have faded away. Future astronomers might never know how the universe began, but we know. We have caught the photons. We have read the message. We have learned that the universe is vast, ancient, and dynamic. We have learned that we are part of a story that spans billions of years. In the next chapter, we will return to the present moment. We will look at the light that is right here, right now. We will look at the meaning of light, how it sets our biological clocks, how it creates the atmosphere of our planet, how it affects our mood and our health. We will explore the connection between light and life. We will see that we are not just observers of the light, we are creatures of it. We run on solar power. For now, think of the ancient photons falling on the roof of your house. Think of the journey they have taken. 13 billion years of flight, dodging galaxies and dust clouds just to end here. They have traveled across the entire universe to reach you, to be part of this moment. You are the destination of the cosmos. We have followed the photon across the desolate expanse of the cosmos. We have watched it dodge galaxies and navigate the webs of dark matter. But now, the journey changes character completely. The photon has arrived at a destination. It has reached the thin, fragile envelope of gas that surrounds our home. It has reached the biosphere. For 13 billion years, the photon traveled through dead space. It encountered nothing but silence and cold. Now, suddenly, it enters a world of noise, warmth, and complexity. It enters a system where energy is not just moving, it is doing work. It is driving the engine of life. The first greeting the photon receives is from the atmosphere itself. We often think of the air as transparent, but to a photon, it is a busy, crowded thoroughfare. As our photon enters the upper layers of the stratosphere, it joins a massive flood of energy pouring down from the sun. If our photon is high-energy ultraviolet light, it meets a heroic end here. It strikes a molecule of ozone, 3 oxygen atoms bound together. The ozone absorbs the photon, sacrificing itself to stop the radiation from reaching the ground. This absorption releases heat, warming the upper atmosphere. It is a global shield, invisible but vital, that protects the DNA of every living thing below from being shattered by the sun's fury. But let us assume our photon is visible light, a packet of gentle yellow warmth. It passes through the ozone safely. It filters down through the troposphere, the layer of weather. It might bounce off the top of a cloud, reflecting back into space. A lost opportunity for Earth, but a beacon for distant astronomers seeing our planet shine. Or it might slip through a gap in the clouds. It rushes toward the surface. It strikes the ground. Perhaps it hits a stone or a patch of dark soil. In this collision, the photon disappears. Its energy is absorbed by the atoms of the ground. They vibrate faster. The ground warms up. This heat then radiates back upward, trying to return to space. But the atmosphere has a trick. The molecules of carbon dioxide and water vapor in the air act like a blanket. They let the visible light in, but they trap the outgoing heat. They catch the thermal radiation and send it back down. This is the greenhouse effect. Without it, Earth would be a frozen ball of ice, with an average temperature of -18 degrees Celsius. Life as we know it would be impossible. Our photon, by dying on the ground, has contributed its tiny spark to the warmth that cradles civilization. It has become part of the planetary climate. But there is a more intimate destiny for our traveler. Imagine the photon does not hit a rock. Imagine it hits you. You are walking outside on a sunny morning. The photon strikes your skin. It penetrates the outer layer of dead cells and reaches the living tissue beneath. Here, it performs a feat of chemistry that is essential for your survival. If the photon carries the right amount of energy, specifically UVB radiation, it strikes a molecule of cholesterol sitting in your skin cells. The energy snaps a chemical bond, breaking the ring structure of the molecule. This transforms the cholesterol into something new, pre-vitamin D3. Over the next few hours, your body's warmth converts this into vitamin D. This molecule enters your bloodstream. It travels to your liver and kidneys, where it is activated. It becomes a hormone that controls the absorption of calcium, building your bones and strengthening your immune system. We are solar-powered in a very literal sense. We do not just eat food, we eat light. For most of human history, we lived outdoors, bathed in this solar nutrition. Today, living in boxes, behind glass that blocks UV rays, many of us are starved of this specific frequency. We are light deficient. The relationship between skin and light is an ancient evolutionary dance. As our ancestors moved out of Africa, away from the intense equatorial sun, their skin grew lighter. They shed the melanin, the natural sunscreen, to allow more of the weak northern light to penetrate and create vitamins. Conversely, those who stayed near the equator kept their dark skin to protect their folate levels from being destroyed by the intense radiation. The map of human skin color is simply a map of the photon's intensity across the globe. We are painted by the sun. But light does more than build bones. It sets the time. Deep in the center of your brain, there is a master clock, the suprachiasmatic nucleus. It coordinates the rhythm of every cell in your body. It tells the liver when to filter, the heart when to slow down, the pineal gland when to release melatonin for sleep. But this clock is not perfect. It runs slightly slower than 24 hours. Left to its own devices, it would drift. To stay accurate, it needs a reset signal every morning. It needs light. For decades, scientists thought this signal came from the rods and cones, the visual cells we use to see. But in the 1990s, they made a startling discovery. They found blind mice with no rods or cones, that still kept perfect time with the sun. How were they seeing the dawn without eyes? They discovered a third type of photoreceptor, a secret set of cells hiding in the retina. They are called intrinsically photosensitive retinal ganglion cells, or iPRGCs. These cells are not for vision. They do not send images to the visual cortex. You cannot see with them. They are not connected to your conscious mind at all. Instead, they send a direct cable to the master clock in the hypothalamus. They are sensitive to one specific color, blue, the blue of the morning sky. When our photon, let's say a blue photon from the dawn sky, strikes one of these cells, it sends an electrical jolt to the brain. This jolt says, "Sunrise, reset the clock, begin the day." The brain responds instantly. It suppresses melatonin, clearing away the fog of sleep. It boosts cortisol, providing a surge of energy. It raises body temperature. It prepares the organism for action. This is why getting outside in the morning is the single best thing you can do for your sleep at night. You are anchoring your biology to the rotation of the planet. You are syncing your internal gear wheels with the cosmic gear wheels. But this system has a dark side in the modern world. We have filled our nights with artificial stars. Our screens, phones, laptops, TVs are backlit by LEDs that are rich in blue light. When you stare at a phone at midnight, you are firing blue photons directly into these time-keeping cells. You are sending a false signal. You are telling your ancient brain that it is noon. The master clock gets confused. It delays the melatonin. It keeps you awake, alert, and wired when you should be winding down. We have polluted our own timeline with junk light. We are living in a state of perpetual artificial jet lag. But when the light is natural, it is a healer. Light affects our mood directly. In the winter, when the days are short and the photons are scarce, millions of people suffer from seasonal affective disorder, SAD. They feel lethargic, sad, and hopeless. Their brains are starved of the serotonin boost that sunlight triggers. When spring returns and the angle of the sun changes, the light intensity increases. The photons hit the eye, and the brain increases serotonin production. The mood lifts, the energy returns. We feel lighter. This is not just a metaphor. Sunlight is a drug. It is a natural antidepressant. We are phototropic creatures, turning toward the light like sunflowers. We seek the sun because our biology demands it. But light is not only something we receive, it is something life can create. If we travel to the deepest parts of the ocean, where the sun's photons can never reach, we find a world of eternal darkness. The water absorbs the sunlight completely within the top few hundred meters. The abyss should be black, but it is not. It is sparkling. Down in the dark, life has learned to make its own photons. This is bioluminescence. It is a chemical miracle. A creature mixes a molecule called luciferin with oxygen. The reaction releases energy, but not as heat. It releases it as cold light. It is nearly 100% efficient. In the deep, 90% of all animals make light. They use it to hunt, to hide, to find mates. Anglerfish dangle glowing lures. Squid spray clouds of glowing ink to confuse predators. Tiny plankton flash when disturbed, creating trails of blue fire in the wake of a submarine. On land, we see it in the firefly, a meadow at dusk filled with blinking yellow lights. This is light used as language. The male flashes a pattern, the female flashes back. It is a conversation made of photons. This biological light reminds us that energy is never lost. It just changes form. The energy the firefly uses to flash originally came from the food it ate, which came from a plant, which got it from the sun. The light of the firefly is just delayed sunlight, repackaged and released by life. Everything flows from the star. But let us return to the human experience. Our relationship with light goes beyond biology. It is emotional. It is spiritual. Think of the feeling of a sunset. The light has traveled through the thickest part of the atmosphere. The blue and green wavelengths have been scattered away by the air molecules. Only the long, resilient red and orange waves remain. They paint the clouds in violet and gold. We stop and watch. Why? Why do we find it beautiful? Perhaps because it signals the end of the day's labor. Perhaps because the warm colors signal safety and fire. Or perhaps it is simply the awe of seeing the mechanics of the planet made visible. Think of the light of a candle. It is distinct from the harsh white of a bulb. A candle flame burns at a lower temperature. It emits mostly infrared light, heat, and a warm yellow-orange glow. This spectrum is gentle on the eyes. It does not trigger the wakefulness signal in the brain. It allows us to relax. It draws us in. For thousands of years, this was the only light we knew after dark. Our stories, our cultures, our families were forged in this small circle of warm light. Today, we are reclaiming that relationship. Architects are designing buildings that maximize natural daylight, knowing it boosts productivity and happiness. Hospitals are installing circadian lighting that changes color throughout the day, blue in the morning to wake patients up, warm amber in the evening to help them sleep and heal. We are remembering that we are creatures of the sun. Even our technology is trying to mimic nature. The screens we use now have night modes that filter out the harsh blue light in the evening, trying to be kinder to our ancient retinas. We are learning to live with the photon rather than just consuming it. As we stand in the flow of this energy, we realize that we are transparent to it. Neutrinos from the sun pass right through the earth and through your body, trillions of them every second, without touching a single atom. Radio waves from distant quasars pass through you right now, carrying the news of black holes, but your senses are not tuned to hear them. You are standing in a river of cosmic information, but you only feel the few drops that your eyes and skin can catch, the visible light, the warmth. But those drops are enough. They are enough to build a world. They are enough to build a mind that can understand the world. In the next and final chapter, we will step back and look at the whole journey. We will look at the meaning of it all. We will reflect on the photon's path, from the crushing pressure of the core, through the thousands of years of darkness, the flight across space, the interaction with the atmosphere, and the final arrival at the eye. We will see that this journey is a metaphor for our own search for meaning. We will look at the impermanence of light, how it exists only in motion, only in the act of giving itself away. We will ask, if the universe is mostly dark, what does it mean that we can see? What does it mean that we are the universe's way of looking at itself? For now, close your eyes again. Visualize the sun setting, the sky turning a deep, bruised purple, the stars coming out one by one. Each star is another sun, sending its own photons on their own long journeys. Some of them will land on your retina tonight, a connection made across light years. You are not isolated. You are the destination of the sky. Rest in that connection. Feel the hum of life in your cells, powered by the light of a star. You are glowing with life. We have traveled from the crushing heart of a star to the silent voids of intergalactic space. We have seen the photon born in fire, trapped in density, liberated by the surface, and stretched by the expansion of time itself. We have watched it navigate the atmosphere and the biosphere, but every journey must have an end. For a photon, the end is not a fade-out. It is a collision, a moment of impact, a transfer of energy. Tonight, we will witness the final second of that 13 billion-year flight. We will see what happens when the light of the universe meets the light of the mind. Imagine you are standing in a quiet garden at night. The air is cool. The sky is clear, a dome of obsidian scattered with diamond dust. You look up. In that simple act of looking, you are opening a door. Your pupil dilates, widening the aperture of your biological camera to capture the faint rain of energy falling from the sky. The photon we have followed, the one born in the blue supergiant eons ago, or the one born in our sun 8 minutes ago, enters your eye. It passes through the cornea, the clear window. It swims through the vitreous humor, the jelly of the eye. It strikes the retina. This moment is the photon's death. It is absorbed by a single molecule of rhodopsin in a rod cell. The energy that was forged in nuclear fusion, that traveled across the void, is suddenly converted into a chemical snap. The protein changes shape. This chemical change triggers an electrical signal. A pulse of voltage travels down the optic nerve. It enters the dark, wet theater of the brain, and there, in the visual cortex, a miracle happens. The electricity becomes an image. It becomes a star. You see the light. The photon has ceased to exist as energy, but it has been reborn as information. It has become part of your consciousness. The universe has touched you, and you have touched it back. This connection is profound. It means that your eyes are the destination of the cosmos. The stars are not just burning in the void. They are burning for Hag, this moment of observation. Without the eye to catch it, the photon would continue traveling forever, a wave without a shore. We are the universe's way of looking at itself. We are the eyes of the galaxy. The atoms in your retina were forged in stars. Now they are catching the light of other stars. It is a closed loop of stardust perceiving stardust. But looking up carries a consequence. It connects us to the past. As we learned, light takes time to travel. The moon is 1.3 seconds ago. The sun is 8 minutes ago. The stars are years, centuries, millennia ago. The Andromeda Galaxy is 2.5 million years ago. When you look at the night sky, you are not seeing the present. You are seeing a collage of different times. You are looking down a tunnel of history. The farther out you look, the further back you see. This creates a concept in physics called the light cone. Imagine a cone expanding backward from your eye into the universe. Everything inside that cone is visible to you. Everything outside it is not. The edge of this cone is the cosmic horizon. It is the limit of what we can know. Beyond that horizon, there are galaxies whose light has not yet had time to reach us since the Big Bang. They are there, but they are not part of our reality. They are causally disconnected. But here is the beautiful thought. The horizon is growing. Every second, light from slightly further away reaches Earth for the first time. Every second, the observable universe gets a little bigger. New stars blink into existence on the edge of our vision. We are constantly inheriting more of the cosmos. However, there is a shadow on this horizon. The expansion of the universe, driven by dark energy, is accelerating. It is stretching space so fast that distant galaxies are being pushed away faster than the speed of light. Their light is trying to reach us, swimming upstream against the expanding river of space. But the river is flowing too fast. The light will never arrive. These galaxies are disappearing from our future. They are fading into the red and then into the black. This means we are living in a golden age of astronomy. We live in a time when the universe is transparent, when the galaxies are close enough to see, and when the sky is filled with stories. In the far distant future, trillions of years from now, the expansion will have swept all other galaxies over the horizon. The night sky of the future Earth will be dark, save for the few stars of our own galaxy. Future civilizations might look up and think they are alone in a static, empty void. They will not know about the Big Bang. They will not know about the expansion. The evidence will have fled. We are the privileged witnesses. We are the keepers of the memory of the universe. But let us return to the present. Let us return to the meaning of the light that surrounds us now. Light is not just a messenger. It is a sculptor. It sets the rhythm of life. The rising and setting of the sun governs the circadian rhythms of every cell in your body. When blue morning light hits your eye, it signals the brain to wake up, to release cortisol, to raise body temperature. When the red evening light hits, it signals the brain to release melatonin, to cool down, to sleep. We are timepieces wound by the sun. Our health, our mood, our energy all depend on this synchronization with the photon flux. We are creatures of the light cycle. Even our atmosphere is a product of light. The ozone layer that protects us was built by ultraviolet photons splitting oxygen molecules. The ionosphere that reflects our radio waves is created by solar X-rays stripping electrons from atoms high in the sky. The weather, the winds, the rain, the hurricanes is driven by the uneven heating of the globe by sunlight. The photon is the engine of the Earth, and deeper still, light is the carrier of force. In quantum mechanics, forces are exchanged by particles. The force of electromagnetism, the force that holds electrons to protons, that holds atoms together, that makes matter solid, is carried by photons. Virtual photons are constantly flying back and forth between charged particles, telling them to attract or repel. The reason your hand does not pass through the table is because of a storm of photons exchanging electromagnetic force. Matter is held together by light. So, the story of light is the story of everything. It is the story of structure, of energy, of information, and of life. But what is the ultimate fate of the photon? Does light live forever? In a vacuum, yes. A photon never ages. It never decays. It can travel for eternity. But the universe is not a vacuum. It is filled with stuff. Eventually, almost every photon will hit something. It will hit a dust grain, a planet, a black hole. When it does, its energy is absorbed. It warms the object. The high-quality energy of the visible light is degraded into the low-quality energy of heat, infrared radiation. This is the second law of thermodynamics. Entropy increases. The universe is slowly converting all its useful energy, its starlight, into waste heat. Over trillions of years, the stars will burn out. The galaxies will go dark. The black holes will evaporate. The universe will enter the dark era. But even then, the photons will remain. The universe will be a bath of long wavelength radiation, radio waves and microwaves, stretching across the ever-expanding void. The light will become dilute. It will become cold, but it will not vanish. The echo of the Big Bang and the echo of every star that ever shined will ripple through space forever. This sounds lonely, but there is a peace in it. It is the ultimate rest. The universe began in a flash of infinite brightness, and it ends in a whisper of infinite calm. Between these two darknesses, the darkness before the Big Bang and the darkness of the heat death, we have this moment. We have the era of starlight. We are here while the party is happening. We are here while the fireworks are exploding. So tonight, as you close your eyes, think of the light. Think of the journey it took to reach you. Think of the fusion in the core, the million-year walk through the plasma, the flight through the cold vacuum, the scattering in the blue sky. Think of the leaf that caught the light and made the sugar that feeds your brain. Think of the eye that caught the light and made the image that fills your mind. You are a vessel of light. Your body glows in the infrared. Your brain crackles with electrical impulses derived from the sun. You are a child of the star. Let this knowledge hold you. You are not separate from the universe. You are woven into it by threads of energy that stretch back to the beginning of time. The darkness of your room is not empty. It is filled with the potential of the dawn. The earth is turning. The sun is there, just beneath the horizon, driving the winds, warming the far side of the world, preparing to return. The light never stops. It only changes direction. Let your own light dim now. Let the visual cortex rest. Let the colors fade into gray, and the gray into black. Sink into the comfort of the shadow. The shadow is just the earth protecting you from the brilliance of the star, giving you a time to rest, to repair, to dream. The photons will be there when you wake up. They will be painting the world anew, refreshing the colors, warming the air. For now, drift in the afterglow. Float in the memory of the sun. Thank you for listening to Dreaming Through Knowledge. May your rest be deep, your dreams be luminous, and your journey be peaceful. Good night.